Right, so I'll share my slides. Right, so this is the live session of the final week of this course, NMR spectroscopy for structural biology. Uh, there will be one more session this coming Monday where it will be kind of like a going over all the classes and solving practice problems related to all the classes. So in this session, the week 12 lectures will be covered, which focuses on solid state NMR. So firstly, what samples can be classified as solids? You know, a very basic thing is that matter is divided into solid, liquid, and gas. And liquid can be of two types, isotropic or anisotropic. Isotropic means that it is uniform in all directions. This is the NMR that we have studied so far has mostly been of this type. So we have been studying solution state NMR where the sample was dissolved in a liquid and it was isotropic in nature. That means that the molecules in the sample was free to tumble and move around, and so all the properties got averaged out and it is uniform in all directions. This is the kind of NMR we have studied so far. The other kind of liquid is called anisotropic. This mainly happens when there is an orientational order. So if you have a liquid crystal, for example, then as you know, crystals always have a repetitive way of packing. So there is a certain fixed arrangement in crystals, and so there is a certain order in the orientation. This is just a representation shown here. You can see that there is a certain order in this compared to the isotropic liquid. So this kind of anisotropy can liquids can also have it and solids can also have it. And this is normally what we see in membranes. So if you imagine a membrane protein, they are oriented at a certain angle. They can pass through the membrane once, they can pass through the membrane several times, or they can even be at the periphery of the membrane. The main common point of all these membrane proteins is that they are oriented at a certain angle. That is, they have orientational order, and so they are anisotropic solids. That is, so solid liquids can be anisotropic and solids can also be anisotropic. Now, solid has two other types of classifications, that is ordered and disordered. Ordered, in the ordered, so what is the difference between anisotropic and ordered? Anisotropy, what we discussed, has short range order. For example, if you look, suppose this yellow part is one kind of order, the red part is another kind of order. So within the yellow part, you have uniformity. Then again, within the red part, you have a different kind of uniformity. So there is only order within the yellow part. But when you go to the red part, again, there is some disorder. So this is called short range order, and this forms anisotropic solids. Ordered solids, on the other hand, have long range order. So ordered solids is exactly like the crystals we have studied so far. So as you know about crystals, they have a unit cell, and the orientation in the unit cell is repeated throughout the crystal, no matter how big the crystal is. So ordered solids basically have long range order, and they can be crystals, but they can also be fibrils, fiber-like solids. And finally, you have disordered solids where there is no order whether it is short range or long range. And under disordered solids, you have glasses. Normally, what we will focus on in the solid state NMR are the anisotropic solids and the ordered solids, that are the crystals and fibrils. We won't look into disordered solids. So that is basically, and gas we don't look at in NMR at all, because in gas, you know, the particles are randomly moving. So the spins are completely randomly oriented due to the fast tumbling of the gas molecules. That makes the net spin quantum number 0, and it is not possible to do any NMR spectroscopy using gas. So gas is studied by other methods which are not covered in this course. In this course, we have so far focused on isotropic liquids, but in this last class, we will go a little bit into solid state NMR. So why is solid state NMR required? So there are many samples which are not soluble. So if the sample is not soluble, then you will not be able to do the solution state NMR we have been doing so far. Or you can have samples where there is no long range order. So what it means by this is that X-ray crystallography, we can only do it for crystals which have a long range order. But you might have a short range order also, which we just discussed here, where order is present only in a small region. For those kind of solids, X-ray crystallography is not valid. So that is another use of the solid state NMR. Normally, the targets of solid state NMR are, they can be protein, micro or nanocrystal. So suppose you have a very small dimension crystal, which is why it's called micro or nanocrystal. So it does not have long range order. It only has a short range orientational order. Then this cannot be studied by X-ray crystallography. You will need to use solid state NMR. Then you can have a protein precipitate which is not dissolving in any solvent. Then again, solid state NMR comes into play because you cannot do liquid state NMR if it is not dissolving in any solvent. Then you can have aggregated proteins. Aggregated proteins, again, they will not be soluble in any solvent. You can have membrane embedded proteins. So suppose you have proteins like the membrane proteins we just discussed here, which behave completely differently in the environment of the membrane. So if you take them out of the membrane environment and dissolve them and then study the liquid state NMR, that is not of much use. You need to study them in the membrane environment. So in that case, again, solid state NMR comes into play. And finally, you can have proteins inside the whole cell. So if you remember, we studied something called STDD NMR. That was often used for membrane bound proteins where you could not separate the protein out from the cell. But that did not give very clear resolution always. So instead, another thing you can do is solid state NMR. Suppose you have a protein inside the cell and you want to investigate the structure of the protein without taking it out and purifying it. That is, you want to do an in vivo investigation. Then again, solid state NMR can come into play and you can study the protein while it is inside the cell itself. So let us look at some of the, we just discussed these aggregated proteins and all. Let us look more into details of that. One thing is that protein misfolding is common in many diseases. So we studied the folding pathway of the protein or the folding funnel. And if you remember, in the folding funnel, there was many local minima. And we had discussed that sometimes the protein can get stuck in a local minima. So it is not able to reach the global minima. This pathway is not possible. So the protein is orienting a structure which is not the native structure of the protein. Then it is called a misfolded protein. And this causes many diseases. And normally, whenever you have a misfolded protein, it starts to aggregate. So you can see here is a picture shown of the aggregation. So if the protein is not in its native structure, it will tend, basically, kind of fibers will form and they will sit on top of each other and form an aggregate. That is what is observed here. Due to this aggregation, the protein as a whole becomes insoluble. Many diseases are caused by this kind of aggregation of misfolded proteins. These include Alzheimer's disease, that is caused by aggregation of the beta amyloid protein misfolding, Parkinson's disease, that is caused by misfolding of alpha synuclein protein, Huntington disease, prion diseases, and even type 2 diabetes, which is caused by misfolding and aggregation of the amylin protein. So, in order to study these proteins, we already discussed these are not soluble in any solvent. So, in that case, solid state NMR is something very important to study how these proteins are aggregating and find out the origin of these diseases in order to come up with a treatment strategy. The other kind of proteins studied by solid state NMR are the membrane proteins, which are like GPCR, ion channels, transporters. So, membrane proteins, we already discussed that in the environment of the membrane, they behave very differently. But if you take it out from the membrane environment, purify it, then dissolve it in some solvent, and study the solution state or liquid NMR, they will give a very different structure. But that structure is not of much use because that is not the actual structure of the protein. The actual structure of the protein is the one that it adopts in the membrane environment. And so, in order to study that, we must simulate the membrane environment and take the solid state NMR. And these membrane bound proteins form 60% of all drug targets because you know that in order for any drug to enter the cell, it has to go through a transporter protein like GPCR. So, many of these membrane proteins are targeted by drugs. So, it is important to understand the structure of these proteins in the native membrane environment, and that is where the solid state NMR comes into play. So, there are many challenges in solid state NMR. Firstly, the resolution is lost. So, here you can see the NMR of this compound in solution shown in blue and in solid shown in red. You can see that in solid state NMR, there is such a huge line broadening that all resolution is completely lost, and you cannot solve the structure from this kind of broad line NMR. This is for 1H. Even for 13C, if you see, the blue NMR that is in solution is very distinct and it very clearly tells you how many different kinds of carbons there are. But in case of solid state NMR, again, everything is very broadened out and you cannot distinguish any peaks. Basically, what happens is that in solid state NMR, there are anisotropic interactions occurring between spins because it is not allowed to tumble. In solution state NMR, the molecules are free to tumble and move around in solution. So all the anisotropic interactions average and cancel out. But that is not the case in solid state NMR. Why we say static solid state NMR, I will come to in the following slides, where we will discuss that how this disadvantage is tackled by dynamism. So I'll come to that. Just think that in solid state, the molecules cannot freely tumble. So the anisotropic interactions cannot average and cancel out. And this is the reason behind such line broadening. So that is one disadvantage of solid state NMR. But there are techniques to overcome this, and we will discuss this in the coming slides. So now let us briefly look into the isotropic versus the anisotropic interactions. Basically, in solids, the interaction depends on orientation of the molecule, and these are called anisotropic interactions. So imagine, suppose you have a molecule. So here, if you're seeing a, suppose this is a solid structure. Suppose this is a solid structure. In different places, the orientation is different. There is short, so in each of these square structures, you have short range order. But overall, there is an anisotropy because there is only short range order. And also because it is a solid, these are not allowed to freely tumble and move around. So we are restricting the motion of the spins. So suppose the spins which are oriented in this red square. They will show a different chemical shift shown by this red peak. The spins in this blue square, they are oriented differently, and we have also restricted their motion, so they are not able to change their orientation. They will show a different chemical shift shown by this blue peak. Similarly, wherever you have a different orientation of the spin, they will give a different chemical shift. Because it is a solid and the spins are not allowed to freely move and average the different orientations out. So because it is a solid, there is restriction in the motion. So each different orientation of the spin will give a different peak. And overall, you will see a broad envelope kind of spectra, which is what we saw in the previous slide. You're just seeing a broad envelope. So in solids, there is a limit to the resolution in NMR spectra of the biological macromolecules. In liquid, what happens? The spins are free to move. So here also spins may be oriented in different directions, like up, sideways, more sideways, and so on. But the difference is that unlike solids, there is no restriction. The spins can rapidly move and tumble around and average themselves out. So suppose this orientation gives a chemical shift here, this gives somewhere here, this gives. So overall, you will see an average chemical shift. Overall, all these three you will not see individually. You will see somewhere in the middle of all these three. Some average chemical shift you will see, because all the spins are freely tumbling and averaging themselves out. So this is called, this is when there are no anisotropic interactions. We will look at this in another way. So we know from quantum chemistry that the Hamiltonian function gives us the total energy. This total energy can be divided into external energy and internal energy. What falls under external? Firstly, you have the static field, that is the spectrometer frequency. The spectrometer frequency excites the spins, and so it is an external source of energy. Then you have the RF field. RF field basically is the pulse that is given to the spins. If you remember the different pulse sequences we studied, we can have 90-degree pulse, 180-degree pulse, so on. So RF field is another external perturbation that is giving energy to the spins. So these are the two external sources of perturbation. Now in the internal perturbations, you can have, or internal energy, you can have chemical shift, you can have dipole-dipole short-range interactions. Now these are the ones that are introduced due to anisotropic interactions. The dipole-dipole short-range interactions are introduced due to anisotropic interactions. You can also have dipole-dipole long-range interactions. These are basically the ones that are used to find the distance constraints in the NOESY spectra. Then you can have J coupling, and finally you can have quadrupole coupling. We don't need to look too much into the detail of quadrupole coupling. One thing you can remember, that in solid state NMR, so let us compare solid, ignore the second one for now, solid with the ice. Solid state NMR is something we are just studying in this class, and isotropic liquid NMR is something we have been studying so far. So this dipole-dipole short range interaction is due to anisotropic interaction. So it is present in solid state, but we just studied in the previous slide that in liquid there are no anisotropic interactions. So this becomes zero. Then the quadrupolar coupling, this is also due to anisotropic interaction. So this also becomes zero in the liquid phase. And even the other, so there are certain interactions that are additional interactions in solid state NMR, which are the dipole-dipole short range interaction, the quadrupolar coupling, and even the chemical shift. You can see it is greater in the solid state compared to the isotropic liquid. So these basically, so you have more contributions to the energy. And this is basically causing the line broadening. In liquid state NMR, what happens? Isotropic liquid, I would rather say. Isotropic liquid, what happens is these additional interactions are cancelled out or they become smaller, and so you have much sharper lines. But in solid state NMR, you have these additional interactions, and that is what causes the line broadening. Anisotropic liquid is somewhere between solid and isotropic liquid. So you can see that you do have this dipole-dipole short-range interaction and quadrupole coupling, but the magnitude is smaller. So suppose in isotropic liquid, you have, just I'll delete this. Yeah, suppose in isotropic liquid, you have a very sharp peak, and in solid, you have an extremely broad peak. Anisotropic liquid will be somewhere in between these, where you have a peak with medium line broadening. Because you do have these additional dipole-dipole and quadrupolar interactions, but they are of smaller magnitude compared to the solid state NMR. So basically, you can see solution state NMR. They are mainly used when the protein or molecule is tumbling very fast. So there can be unfolded proteins or there can be folded proteins, but as long as they are in a solution environment, they will tumble very fast around nanosecond correlation time, and that forms part of solution state NMR. But if the protein forms a micelle, so micelle means that the protein is in a lipid bilayer or lipid shell. So the size of the particle is increasing. As the size of the particle is increasing, the correlation time will decrease to around microsecond. Now the size of the particle can increase even further. It can be part of a lipid bilayer. So this is kind of like a membrane protein which is embedded in the lipid bilayer. So this has a huge size. So there is a huge restriction in the protein dynamism, and the correlation time becomes of the order of millisecond. This is the case where the solid state NMR comes into play. Now there are several tricks to remove the challenges faced in solid state NMR. One is to mimic the inherent averaging process in solution state NMR to obtain high resolution isotropic information. So we already discussed that because of the fast tumbling in solution state NMR, all the anisotropic interactions are averaging and cancelling out. So somehow if we can mimic that in solid state, we will be able to obtain high resolution spectra in solid state NMR also. To do this, there are mainly two goals. Firstly, we have to remove the anisotropic part and retain only the isotropic part. So if you see in the previous slide, the anisotropic parts are the dipole-dipole short-range interaction, the quadrupolar interaction, and the chemical shift anisotropy also. If we can somehow remove them to mimic the isotropic liquid, we will be able to get this kind of sharp peak for solid state NMR also. This is called decoupling or averaging of interaction. The second goal is to, after getting a sharp spectra, we have to get back the anisotropic part so that we can find out the geometry parameters. So basically what happens is that each of these anisotropic components, they are very important to find out the orientation or geometry of the molecule. For example, the chemical shift anisotropy, the quadrupolar coupling, dipolar coupling, J coupling, each of these gives very vital and crucial information about the geometry of the molecule. So if we remove these in order to get a sharp spectra, we will be losing out a lot of information on the geometry of the molecule. So initially we have to remove them so that we get the sharp spectra. But somehow we have to get the information back so that we do not miss out on any of the geometry parameters that we get from these coupling information. This is called recoupling or reintroducing the full interaction. So these are the two goals of solid state NMR. So first, now we will talk about a concept called magic angle spinning or mass. Basically, in solution state NMR, we know that the sample tube was placed along this B0, the external magnetic field. But in solid state NMR, what is done is that there is a kind of, this is called a rotor. It looks like this. Basically, the sample is placed inside this rotor and it is spun at an angle of theta m, which is called the magic angle. And as it is spinning faster and faster, all the anisotropic interactions are averaging out. So what is this theta m? Basically, the dipolar coupling term is given by 3 cos square theta minus 1. If we assume this dipolar if we take this dipolar coupling term to be 0, we will get a theta of 54.7 degrees. So if we rotate the sample placed in the rotor at this angle, 54.7 degree, the dipolar coupling becomes 0. So you're averaging out the dipolar coupling, that is the anisotropic interaction. So averaging out the anisotropic interaction should give you a sharp spectra. Indeed, that is what happens. If we look at the simple molecule of glycine, the spectra shown on top is the static NMR, means you are not rotating this tube. We are just taking the normal static solid state NMR. So in this compound, there are two carbons. One is this C alpha, another is this CO attached to O. So just I'll escape once. So there are two carbons here, 1 and 2. Indeed, you can see two very broad peaks belonging to this C alpha and CO. Now slowly the speed of rotation of this rotor is increasing. You can see omega is the rotational frequency, and it's just given by 2 pi is a constant, and you are increasing the frequency from 0.85 hertz to 3 hertz to 5.5 hertz to 12 hertz. As the frequency is increasing, the lines are becoming sharper and sharper till at 12 kilohertz, not hertz. Till at 12 kilohertz, you have very sharp single line, well resolved spectra. So each carbon is shown by a single line. So this is similar to what you would expect from solution state NMR. Basically, what is happening, as you are increasing the speed of this rotation, the dipolar coupling term and other anisotropic interactions are all cancelling out. And if you cancel out all the anisotropic interactions, it will behave like solution state NMR and you will get very well resolved sharp lines. So this is how the at disadvantage of solid state NMR, that is the line broadening, is tackled. Now these rotor can have different diameters. The outer diameter determines the maximum rotation frequency. The smaller diameter that you will have a greater frequency of rotation. And so you will have greater resolution. So if you have a large protein, it is always better to take a rotor of small diameter so that you can spin it at very fast speeds and you can get better resolution. The inner diameter of these rotors, that determines the sample volume. So you can see that a small rotor will not be able to hold much of the sample, but in the large rotor, you will be able to fit a lot of the sample. So that is how the disadvantage of solid state NMR is tackled, by spinning the sample after keeping it at a rotor, and the sample is spun at an angle of theta m, that is the magic angle. And the value of theta m is 54.7 degrees, because at this angle, the dipolar coupling term is cancelling out. So now we will look at something called heteronuclear dipolar decoupling. Basically, what happens? Suppose this is a compound and you have both 1H and 13C. Now, 1H is an abundant spin. We know that the natural abundance of 1H is very high, around 99% or so. So we are calling it the abundant spin, and it is shown by these green circles. 13C, we are calling it the rare spin because the abundance of 13C in nature is only 1.1%. So this red spin is 13C, or 15N is also low natural abundance. So it can be 15N also. Now you can have coupling bit from 1H to 1H shown by this green line, which we are calling as homonuclear dipolar coupling because it is between two of the same nucleus. And you can have coupling from carbon to hydrogen, that is heteronuclear dipolar coupling because it is between two different nuclei. Now this is when the sample is static. Now if you put the sample in the rotor and spin it at the magic angle, so magic angle spinning or mass, what mass does is that it weakens both the coupling, both the homonuclear dipolar coupling and the heteronuclear dipolar coupling is weakened. After that, what is done is that we selectively irradiate the protons. So selectively an RF pulse is given to the protons with a series of decoupling pulses to get rid of the heteronuclear coupling. So selectively all the protons are irradiated. We won't go into the details of the pulse sequence. We are just calling it a series of decoupling pulses. And what that is doing, it is cancelling out all the heteronuclear coupling. So decoupling of the heteronuclear dipolar coupling, and you only have homonuclear dipolar coupling, which is weakened by mass. So here briefly the pulse sequence is shown. Basically, you start from 1H, you selectively irradiate the 1H, and then the polarization gets transferred to 13C, and the final FID is detected on 13C. Basically, why we need to do this is because of this coupling, the lines are getting broadened. So if we manage to decouple it, the lines will become sharp. And we already know that the shorter the distance between two nuclei, the stronger is the coupling. So we can see 1H 13C distance is the shortest. There are many 1H 13C distances which are very short. So the coupling between them will be very strong. You can see here it's 23.0 kilohertz. So if you that is why this heteronuclear coupling, it is important to remove that, and that is what is done here. So heteronuclear coupling is leading to resolution. So by reducing the firstly by magic angle spinning, and then by selectively irradiating the protons with RF pulses, you are basically increasing the resolution. So initially, if the spectra was like this, after mass and RF decoupling, you will get a much sharper, well-resolved spectrum. In addition to this, another thing is done, which is called cross-polarization. In cross-polarization, first the 1H is excited by a 90x pulse. After that, the 1H and 13C are simultaneously polarized by applying RF. So in this region called CP, RF pulses are applied to both 1H and 13C, and they are simultaneously polarized. After that, the pulse is transferred to 13C and the FID is detected there after decoupling the 1H. So what this cross polarization does is that, so we are detecting on 13C. So This earlier picture was the same thing, but you don't have this cross polarization section. So basically you can imagine that in the earlier pulse sequence, an additional cross polarization section is introduced. So why is this introduced? So when we are detecting on 13C, we have to remember that the gyromagnetic ratio of carbon is 1/4 of that of hydrogen. So hydrogen is a much more sensitive nucleus than carbon. So if we are detecting the FID on 13C, 13C is not that sensitive. So we will not get very well resolved peaks. But what we can do is that if we do this cross polarization, then the sensitivity of hydrogen is kind of transferred to 13C, and that will increase the sensitivity of the 13C channel where we are detecting the FID. So if you uh, uh, like omega, for this, what is done is that the frequency of the rotor, we saw the rotor for magic angle spinning. What frequency should this rotor be rotating at? This frequency is set at omega r, the frequency of the rotor. We set it at delta omega h minus delta omega c. So if we set the frequency of the rotor at that value, then the cross polarization will uh, lead to transfer of the polarization from hydrogen to carbon in order to enhance the sensitivity of carbon. So basically, magic angle spinning is helping in resolution. So if you have a broad spectra, it is a combination of magic angle spinning and RF decoupling is helping in resolution. So if you have a broad spectra, it will give you a sharper spectra. And introducing the cross polarization pulse sequence in between this mass and RF decoupling, what that will do is it will increase the sensitivity at carbon. So suppose you have a very low intensity signal. You are not able to detect it in carbon because the gyromagnetic ratio of carbon is only 1/4 of that of hydrogen. But if you include this cross polarization pulse sequence, basically the polarization gets transferred from hydrogen to carbon, and that increases the sensitivity of carbon. So even though you're detecting on carbon, the cross polarization sequence makes the NMR very sensitive. So if there is a very low intensity signal, it can still detect that. So these two things, cross polarization or CP and mass or magic angle spinning, are basic building blocks for solid state NMR experiments. So you can see here, this is magic angle spinning. Once you do magic angle spinning, followed by proton decoupling using RF pulses, and you detect on carbon after cross polarization. Then you can see here the liquid state and solid state spectra are very similar. The liquid state is shown in blue, the solid state is shown in red. You can see both are giving very sharp, well resolved peaks. So using these techniques, you have managed to gain higher resolution, and you have also, if you increase so this is only with magic angle spinning. In addition to this, if you include, you can see this example. Just one second before I come to that. So if you include magic angle spinning, you will get higher resolution. You can see the resolution of the solid state is almost equal to that of the solution state NMR. The disadvantage is still that it is lower sensitivity because you're detecting on 13C. You can compensate this to some extent by doing the cross polarization pulse sequence so that you increase the sensitivity of the 13C detection. You can also compensate in another way, that is by using larger samples, taking around 30 to 40 milligrams of sample in a 2 millimeter or 4 millimeter diameter rotor. Also, the recording time can be increased compared to solution state NMR in order to increase the sensitivity. So you can see here that if you have a solid state spectra where you have not done mass and you have not done RF decoupling. It is very broad. Sorry, that is the lowest spectra. The lowest spectra is one where you have no mass and no decoupling. It's an extremely broad spectra. The second spectra is one where you have done magic angle spinning but no decoupling. So it is starting to get resolved, but it is still not very well resolved. And this uppermost spectra is where you have done both mass and decoupling. That gives you a very sharp, well resolved spectra similar to that of liquid state NMR. Now, here an example is shown. You have a mixture of two compounds. This first compound, the carbons are shown by this blue lines. And in the second compound, the carbons are shown by this red. In the first compound, the carbons are shown by the blue numbers. And in the second compound, the carbons are shown by this red alpha and beta peaks. So the lower spectra is one where you have done where there is direct polarization. That means you have just applied 90-degree pulse on 13C and you have collected the FID. So you can see in case of direct polarization, that is you have just applied the pulse on carbon and collected the FID like in liquid state NMR, you get a very broad spectra with no resolution. You cannot figure out that which peak belongs to the first compound, which peak belongs to the second compound. But if you do cross polarization, that is what happens in cross polarization is that you first excite hydrogen, then there is a portion where the cross polarization pulse sequence where the polarization is transferred from hydrogen to carbon, and then the detection is on carbon after decoupling the hydrogen. So by transferring polarization from hydrogen to carbon, you are enhancing the sensitivity of the carbon. That is, the signal enhancement is more or less equal to the ratio of the gyromagnetic constants. So once you do cross polarization, you can see that the signal is getting very well resolved and you can clearly find out that which peak belongs to the first compound, which peak belongs to the second compound. So that is the advantage of cross polarization over direct polarization. So far we have studied all about decoupling. So if you look back at the goals, goal 1 is covered, where we are removing or decoupling the anisotropic interactions to increase the resolution and the sensitivity. Resolution was increased by magic angle spinning. Sensitivity was increased by cross polarization. Now we come to goal 2. That is, we have to get back the anisotropic parts so that we can fully elucidate the geometry parameters. So this is what we are calling recoupling of interactions in solid state. We have to selectively reintroduce the anisotropic interactions between the spins. So imagine these were the anisotropic interactions which got cancelled out. So you can see A, B, and C, the three spins are now uniformly oriented. They are kind of isotropic in nature because you have decoupled the anisotropic interactions. You have to reintroduce the interactions so that A, B, and C are oriented as it is in the natural environment, that is with their anisotropic interactions. So they have to be reintroduced, and this is called recoupling. So suppose we have two spins, one around 30 ppm and one around 170 ppm. Sorry, one around 50 ppm and one around 170 ppm. Then the difference in frequency between these two is 120 ppm. And we know that in a 600 megahertz instrument, the resonance frequency of carbon is 150 megahertz. So if the difference of frequency between these two is 120 ppm, we can convert it into hertz by multiplying by this resonance frequency of carbon, that is 150, and we get around 18,000 hertz. So the difference in hertz between the two peaks is 18,000 hertz or 18 kilohertz. So in the magic angle spinning, if we spin the rotor containing the sample at a rotational speed that is matching with 18,000 hertz or half of 18,000, that is 9,000 hertz, then the two carbons will decouple. This is what we were doing so far. We were spinning the rotor containing the sample at speeds after calculating this frequency difference, and after spinning it at those speeds, the decoupling was happening. Now we have to recouple uh, so that we get the anisotropic interactions back, so that we can find out the geometry of the orientations of the protein or other molecule. So one method of doing that is called redoor recoupling, or in full, recoupling of heteronuclear dipolar couplings is rotational echo double resonance. So REDOR stands for rotational echo double resonance. We will briefly discuss the pulse sequence. Just one second. So first, the proton is excited with a 90-degree pulse. Then, this is the recoupling sequence. We apply what is called a two-phase alternating 180-degree pulse every tau rotational rotor time period. So there is a time period called tau rotational. You can see here this time period. And for every time period like this, we are applying 180-degree pulses. You can see pi, this is a 180-degree pulse, this is a 180-degree pulse. And these pulses are alternating in phase. So for every tau rotational time period, two phase alternating 180-degree pulses are applied. So you apply a series of pi pulses on carbon, and in between this series somewhere, an additional pi pulse on proton is applied. What this entire pulse sequence does is that it averages out the effect of magic angle spinning on the heteronuclear dipolar coupling. So what magic angle spinning was doing is that it was reducing the, you can see this heteronuclear dipolar coupling. After magic angle spinning and RF decoupling, the heteronuclear dipolar coupling was completely disappearing. What this pulse sequence does is that it reintroduces back the heteronuclear dipolar coupling by averaging out the effect of magic angle spinning. We don't need to go into the details of how it does that. You just need to remember that this pulse sequence that is there, it kind of cancels out the effect of magic angle spinning, so that again you get back the original situation where you had both homonuclear and heteronuclear dipolar coupling. So that is one way. Another way is called as proton driven spin diffusion. So PDSD, proton driven spin diffusion, or also called as second order recoupling for polarization transfer. Basically, you have uh, so again, we don't need to go too much into the pulse sequence. Basically, what happens is that there is spectral spin diffusion, that is, the longitudinal magnetization is exchanged between dipolarly coupled nuclear spins of roughly the same energy via flip-flop transitions. Basically, the magnetization is transferred from 1H to 13C using the cross polarization. So initially you are applying a pi by 2 pulse on 1H. Then using the cross polarization, so the magnetization is on 1H. Because of this cross polarization segment, the magnetization is coming to 13C. And in 13C, basically you are giving a certain time. This you are calling as the T1 evolution time. And in this time, if you introduce this time, so this will become, let us first consider without this time. So I'll just discard this. Right. So you're starting with a pi by 2 pulse on one edge. Then cross polarization is done to transfer the magnetization to 13C. And then you have a series of TPPM, means these two phase alternating 180-degree pulses that is applied, that kind of recouples the heteronuclear dipolar coupling. And during this recoupling, now we can study carbon-carbon correlations, because how the recoupling is introduced is that, after recoupling, so imagine this is an amino acid. So this is your, this is a peptide. You have your I amino acid, I minus 1 amino acid. All the carbon hydrogen carbon hydrogen correlations, the heteronuclear dipolar correlations, were completely removed by decoupling. But after this proton driven spin diffusion sequence is done, they are again reintroduced. So these black lines that you see, hydrogen to carbon, then carbon to carbon, then again carbon to the next carbon, these all come back when you reintroduce the recoupling. So this recoupling that you're introduced by adding the two phase alternating 180-degree pulses, what the reintroduction of is that it enables a transfer of magnetization from hydrogen to carbon, from carbon to the next carbon, or from the carbon to another hydrogen. So we can now study the carbon-carbon correlations, because you are allowing this time t for the 13C magnetizations to mix. And once the 13C magnetizations are mixing, that is, the spins are diffusing, you are able to study the 13C correlations. So similar to TOXI or NOSI, we will be able to find, like TOXI, we can find out the connectivities within the same amino acid, or we can find out the connectivities with the adjacent amino acid, like in HSQC, or with even longer distance amino acids, like in NOSI. So this mixing time that we are additionally adding is reintroducing or recoupling what we had previously decoupled. And then after this, we can collect the FID. So, and once more, I will discuss. Initially, a pi by 2 pulse is applied on one edge. During the cross polarization pulse sequence, the magnetization is transferred to 13C. Now, after it is transferred to 13C, what was done previously is that you transfer to 13C and then you immediately detect the FID while decoupling. So that was when we had decoupled the heteronuclear dipolar coupling. But now we are reintroducing the heteronuclear dipolar coupling. So now what is done is that after the magnetization is transferred to 13C, we are not decoupling it, but we are giving a T mix. That is a time for mixing of the magnetization of the 13C. During this time, what happens is that the magnetization can transfer from one 13C to the next 13C of the same amino acid, or to the 13C of the previous amino acid. Or if you allow even more time for mixing, the magnetization can transfer to the 13C of some other amino acid that is close to it in space. So basically, if it is within the same amino acid, you will get the TOXI information. If it is with uh, adjacent amino acid, you will get HSQC or other information. And if it is with an amino acid that is not connected to it but is close to it in space, you will get the NOSI information. Either way, after all the magnet spins are allowed to mix and you study the CC correlations, finally you can decouple the protons and collect the FID, so that the final spectra that you obtain is also well resolved. Now, how this spin diffusion is happening? Basically, as I said, the magnetization is exchanging between dipolarly coupled nuclear spins. That means these adjacent spins, or it can be dipolarly coupled through space, of roughly the same energy via flip-flop transitions. We don't need to go into the detail of that. You can just remember that the mechanism is called flip-flop transition. And we are detecting on 13C, but because we have used the CP or cross-polarization pulse sequence, we are enhancing the sensitivity of 13C by transferring the magnetization from one edge using the CP pulse sequence. This is one way. Another thing is that before the mixing, if we introduce a certain time, so in between the cross polarization and the mixing time, if we introduce a time t1, that is the evolution time, then you will have two time axes, t1 where evolution time and t mixing, also called t2. Then you have two time axes and you will be able to get a 2D experiment. So you can see here, basically, before we come to 2D, I'll discuss 2D in just one slide. We'll just look a little bit more into what we saw just now. Uh, so you have a 90-degree pulse sequence on hydrogen. Now, in this pulse sequence, the duration of this pulse sequence is 2.5 microsecond. The power of the pulse is defined as 1 by 4 times the duration of the pulse. So 1 by 4 times 2.5 and 2.5 microseconds, so into 10 to the power minus 6, which will go in the numerator as 10 to the power 6. This you will find out, this will equal to 10 to the power 6 by 10, that is 10 to the power 5 hertz or 100 kilohertz. So 100 kilohertz is the power that is written here. Similarly, after this 90-degree pulse, the cross polarization pulse sequence is applied to transfer the magnetization, the polarization from hydrogen to 13C. The duration of this pulse is 700 microsecond. And we know that for cross polarization, we have to set the frequency of the rotor as the omega hydrogen minus the omega carbon. And omega hydrogen here is 67.5 kilohertz, omega carbon is 50 kilohertz. So the omega rotor during the cross polarization should be 17.5 kilohertz. This omega R is applied during the mixing time. So we have already discussed that we give a time called the mixing time for the 13C magnetizations to mix so that we can get the CC correlations. So whatever we calculate as the omega R, that is the difference in omega of hydrogen minus omega of carbon, we find out to be 17.5 kilohertz. This is the omega R that is applied during the mixing time. So now if we vary the mixing time, we will get different kinds of correlations. If we give a very short mixing time like 20 milliseconds, then we will get only short range correlations that is directly connected. So C alpha to C beta to C gamma, so on. If we give medium range mixing times like 150 millisecond, then we will get correlation with the neighboring residue, like from C beta to the C prime of the previous residue, or C alpha to the C prime, or C alpha to C alpha of the I minus 1 residue. And if we give very long range mixing times like 500 to 800 millisecond, we can get nosy correlations, that is through amino acids that are not directly connected but are close together in space. We can even get that information by increasing this mixing time. Now, what were we talking about is that if we introduce another time axis T1 or the evolution time before the mixing time, then we can also have 2D experiments. That is what I will go into here. Just give me 2 seconds. Right. So 2D experiments, we already know they have a preparation time and a mixing time, which is separated by a evolution time that we are varying. So there are two time axes. One is the evolution time T1, and then is the detection time or the FID that is collected, that is T2. So if we do Fourier transform along both the axes, we get the 2D spectra that we know, where there are from the two time axes, there are two frequency axes, and we will get cross peaks between the two frequency axes. So now if we introduce the T1 time or evolution time before this mixing time, that gives us two time axes and we'll get a 2D spectra. So you can see here, initially we are doing the magic angle spinning, that is the decoupling sequences, and we are getting sharp peaks. So this is the 1D spectra, and we know 1D spectra is equal to the 2D spectra if we only look at peaks along the diagonal. Now we introduce the recoupling by PDSD, that is proton driven spin diffusion. When we introduce the recoupling, we will be able to find carbon-carbon correlations. So you can see we are getting um, uh, cross peaks that are not on the diagonal. We are getting off diagonal cross peaks, and these are giving us the carbon-carbon correlations. Because during the proton driven spin diffusion, we are allowing time for the carbon-carbon spins to mix. And because of this, now we can find correlations between different carbons, and we can extract spectral information after the recoupling. You can see here different 2D correlation spectra in solid state NMR are given. First, we have the 2D 13C spectra. So as we saw in the basic sequence, we first polarize all the proton, then using cross polarization, the magnetization is transferred to 13C. Then in 13C, you give an evolution time T1 and then a mixing time so that the carbon-carbon spins can mix. So if the mixing time is short, it will only give you the correlations to carbons that are directly connected, like C alpha to C beta to C gamma, that is the toxi information. If you give longer time, then it will much longer time, then you will even get information similar to nosy. That is, you can get C alpha to C beta to C gamma to C delta to even the neighboring residues. Neighboring residues can be adjacent in the amino peptide chain, or they can be separated by space depending on the mixing time you give. So that is how you get different peaks of diagonal peaks correlating different carbons, which can be directly attached like C alpha, C beta, or they can be in the neighboring residue like we saw between C alpha of I to C alpha I minus 1 and so on. Another correlation is the 15 and 13C spectra. Here each peak is giving you idea about one amino acid, because in each amino acid you have only one NC alpha, and this is showing the NC alpha correlation. So this is similar to the HSQC spectra in the liquid state. If you remember, in the HSQC spectra, we got NH alpha correlation, NH correlations. So for each amino acid, we will have one peak in the HSQC spectra. Similarly, in the 2D 15 and 13C spectra, we will get one peak for each amino acid. Now, here you can see 13C with 13C, 15N with 13C. You can also get correlations with 1H. So 15N 1H, you can also have correlations, or 13C 1H, you can also have correlations. The problem in these is that the 1H line width is very broad. You can see here it's 120 to 250 hertz. Here it's 150 to 350 hertz. So 1H chemical shift in the y-axis. You can see all the peaks are very much elongated along the y-axis because the 1H line width is so large. This is because the dipolar coupling cannot be averaged out completely due to insufficient rotor speed. So we know that the dipolar coupling in 1H is very strong. So the rotor speed that is needed to completely average out the dipolar coupling is very high. And we cannot use that much high rotor speed due to limitations of the instrument. So we are not able to completely cancel out the dipolar coupling in the 1H, and this causes line broadening in the 1H, which you can see by the elongation of the peaks along the y-axis, that is the 1H axis. Because of this, many of the peaks you can see are overlapping, that is the resolution is poor and the assignment is becoming difficult. So instead of the 1H 15N spectra, we prefer the 13C 15N spectra, where you can see the peaks are much sharper. Similarly, instead of the 1H 13C spectra, we prefer the 13C 13C spectra, where we don't have this kind of overlapping and loss in resolution. So these are different examples of 2D correlation spectra in solid state NMR. Here some more examples are shown. So suppose you have, here we can see some examples of 13C 2D NMR in solid state. So if you have threonine, you can see threonine here. Correlations are seen from, so this is alpha carbon to beta carbon to gamma carbon. You can see alpha to beta to gamma for threonine. Then you have isoleucine. In isoleucine, you have alpha to beta to gamma. There are two gammas, and then you have delta. You can see for isoleucine, alpha, beta, there are two gammas, gamma 1, gamma 2, and then delta. Similarly for lysine. So you can, by assigning each of these peaks, we can find out the order of the amino acids and which are the amino acids that are present in the protein. Then you can have something which is similar to the triple resonance experiments that we studied in solution state NMR. But here we don't use 1H. If you remember, in solution state NMR, we had experiments like HNCA or HNCO, where 1H was also used. But we just saw in solid state NMR, using 1H is a disadvantage because we cannot completely cancel out the dipolar coupling. And so the line widths broaden and there is overlapping and loss in resolution. So for sequential assignment in solid states, these experiments are done, but we do not use 1H. So like, for example, there can be an experiment like NCACB. So the magnetization is transferred from the amide nitrogen to the C alpha to the C beta. Or you can have NCOCACB. So from amide nitrogen, you are not detecting the carbonyl carbon, but you're just using it for transfer of magnetization. So NCO is in bracket because you're not detecting it. You're just using it to transfer the magnetization. And then you're going to Ca and then Cb. Or you can have CaNCOCA. So starting from C alpha, you can jump to N of the I plus first residue, and then from this N you can go to the C alpha of the I plus first residue again. So this is correlating the C alpha I plus 1 and N I plus 1. So these are different 3D experiments that can be done in the solid state. So we will look at some heteronuclear 2D experiments like NCA and NCO. Since we are not utilizing 1H, we in solution state NMR, we used to call it HNCA or HNCO. But now we will call it NCA and NCO because we are not utilizing 1H. So in NCA, what happens is that you start from the amide nitrogen, and it is transferred to the C alpha of the same residue. You can excite, so why NH is shown in blue is because you are exciting the proton. but you are not detecting the proton. The proton is simply transferring the magnetization from proton to the amide nitrogen, which is being detected, and then to the C alpha of the I residue, same residue, which is being detected. So you are detecting only NC alpha. So you will get a 2D spectra where on one axis you will get a 2D spectra where on one axis you have N, one axis you have C alpha. In NCO, what happens? Again, you are starting from the amide hydrogen, but you are not detecting it. That is why it's seen in blue. It is coming to the N, but in NCA, it was going to the C alpha of the same residue. Now it is going to the C prime of the previous residue. So that's why it's called NCO, because you're detecting the CO carbon. So this is giving I minus 1 correlation. So if you do this, then you will get N versus CO. So these are called 2D experiments because you're detecting two nuclei, and they are heteronuclear because one is nitrogen, one is carbon. So again, we don't need to look into the pulse sequence too much. We will just look at the basics. So first, the proton is excited using a 90-degree pulse. Then using the cross-polarization sequence, magnetization is transferred from proton to the 15N channel. Then the 15N spins are allowed to evolve for a time period of T1 after the 13C and 1H are decoupled. Then a second cross-polarization pulse sequence is used to transfer them. So from proton, it comes to nitrogen. In nitrogen, it is evolving. Then from nitrogen, it is transferred back to carbon using another cross-polarization. And finally, the detection is on carbon. So one time axis is on nitrogen, one time axis is on carbon. That is why it's giving you 15 and 13C spectrum. So here some of the heteronuclear 2D or 3D experiments are shown. They are all starting from the hydrogen, but you are not detecting the hydrogen. So this is called NCACX because the magnetization is transferred from N to C alpha, and from C alpha it can go to CO, or it can go to C beta, C gamma, so on. Depending on the amount of mixing time you give, that is how many correlations you will get. Longer mixing time will allow you to get longer correlations, and shorter mixing time will get shorter correlations. One thing, in the PTSD we studied, if an additional pulse is applied to 1H, which is of the order of the spinning frequency or half of the spinning frequency, then it can further assist with the recoupling. And then this is called dipolar assisted resonance recoupling, or DAR. So DARR has a similar pulse sequence, but one more additional pulse is given on 1H. So basically, if you have an additional pulse here on 1H, that will help to recouple faster, and that is called dipolar assisted resonance recoupling, or DAR. So both PDSD and DAR are methods for recoupling. Right. Then there is an experiment called NCOCX. So here from N, you are going to C alpha of the same residue. In this experiment, you can go from N to CO of the previous residue, I minus 1 correlation. And then in the previous residue, it can go to CX, meaning CO to C alpha to C beta, and so on. Then there is an experiment that starts from C alpha, goes to N, and then via CO, so it is not detecting CO, it is just going via CO. It can go to C alpha, C beta, and so on. So this is I correlation. This is I minus 1. This is also I minus 1. So different experiments like this can be designed in order to get different correlations. Now, once you have, so basically similar to the solution state NMR, if you have a knowledge of chemical shifts, if you know where the chemical shifts of each amino acid is coming, so we know glycine will only have, see, this is glycine, there is only C alpha. There is one C alpha that is shown by green here. You can see green is C alpha. Alanine, threonine, and serine will only have C alpha and C beta. So if you come to alanine here, C beta is blue. So you only have C alpha green and C beta blue. Threonine is here. Sorry, not threonine. Not threonine. This is wrong actually, because threonine also has C gamma. Serine, if you look at serine, serine has C alpha, C beta only. Most other amino acids will have C alpha, C beta, C gamma, and so on. The aromatic amino acids are more difficult to identify only from here. So here we are looking at ppm ranges 10 to around 670. For aromatic amino acids, we also need to look at the ppm ranges in the aromatic region so that we can distinguish between tryptophan, histidine, tyrosine, and phenylalanine. So basically, if we have an idea of where the chemical shift appears for each amino acid, then we will be able to assign the spectra of a protein easier. And similar to what we studied in the solvent state NMR, we can do secondary structural analysis from this. So we can, if you remember, we can calculate delta delta, that is the difference in chemical shift of our protein with random coil chemical shift. So here what is plotted in the y-axis is delta delta C alpha minus delta delta C beta. That is the difference in chemical shift of C alpha with the random coil and the difference in chemical shift of C beta with the random coil. They are subtracted from each other and plotted. If this value is negative, that indicates there is a beta sheath secondary structure. You can see in this amino acid shown here from residues 37 to around 137, there are many regions where this delta delta C alpha minus delta delta C beta is negative. All these regions are beta sheaths. You can see shown by these arrows. And there are segments in between the beta sheaths where the value of this delta delta C alpha minus delta delta C beta is either 0 or it is positive. Those are generally turn segments that are linking the different beta sheaths. So secondary structure analysis can also be done from solid state NMR. So here you have a structural model shown of a back-to-fill in back A. And so what we saw here, basically doing the secondary structural analysis, we can find out that it's mostly a beta sheath structure. And in order to find out the three-dimensional structure, we can do PDSD. And we just discussed that in PDSD, if we give the mixing time of 500 to 800 milliseconds, then we will get correlations between carbons that are near to each other in space. So you can see, suppose a carbon this that is connected by this dotted red line, these carbons are close to each other in space. So they will so imagine in solution state NMR, they might have shown nosy cross peaks. In solid state NMR, if you do PDSD and you give a mixing time of 500 to 800 milliseconds, you will be able to get correlations between these two carbons or these two carbons. That is, carbons that are not attached to each other directly but are close to each other in space. So the same information that you get from nosy, you can get from PDSD if you give a long enough mixing time. You can see here, this is a cross peak between isoleucine 100 and isoleucine 117. So they are separated by 17 amino acids, but you can still see the cross peak because the chain is folding and they are coming close to each other. So that is all about this basics of solid state NMR of the proteins. Just give me a couple of minutes. So we will talk about aggregation, which is a generic property of proteins. Proteins, suppose they can have many different native structures like alpha helical, beta sheet, or even those that are intrinsically disordered. Now, these proteins, if they partially unfold, they can form an intermediate called an amyloidogenic intermediate. And this intermediate can form many kinds of aggregates. You can have amorphous aggregates, which are powder-like, or you can have pore-like aggregates. So these pore-like aggregates, if they come on a membrane, they will cause the membrane to have pores. So this is toxic for the membrane because they will kill off the membrane. And further aggregation can even form different fibers called amyloid fibrils. And SEM and TEM studies have shown the fibrillar nature of these aggregates. So this type of aggregation is a very generic property of proteins, and any protein can form this kind of aggregate as long as they misfold. So again, we talked about the folding funnel. If the protein gets misfolded into an intermediate structure, which aggregates, then that can be very toxic for the body and is the origin of many diseases. We can see the structure of the amyloid, these fibers, the amyloid fibrils. They have fibrillar structure. And if CD and FTIR shows that these fibrils aggregate into beta sheet-like structures. So what we saw is that these fibers are aggregating into beta sheets. Now these beta sheets can be arranged in many different ways. So the secondary structure you can see is just beta sheets along the amino acid chain. Each beta sheet is represented by an arrow. In the tertiary structure, many of these beta sheet chains are coming together. You can see this is a parallel beta sheet. This is also a parallel beta sheet. In quaternary structure, one beta sheet is folding over another beta sheet. You can see this is called a parallel cross beta unit because lower beta sheet, if you see, they are parallel. Upper beta sheet is also parallel. That is why it's called a parallel cross beta unit. Or they can be an anti-parallel cross beta unit. If you look at the lower sheet, the yellow is pointing this side, green is pointing this side. So the beta sheet is anti-parallel. The upper beta sheet is also anti-parallel. So this is called the anti-parallel cross beta unit. So this is quaternary structure. So like this, the aggregation forms. Initially, you might have only one beta strand, but multiple beta strands come together to form beta sheets. And one beta sheet can fold over another beta sheet to form quaternary structures. So like this, the aggregation keeps happening. And when this we will look at a protein that forms this kind of amyloid fibril, which is the synuclein protein. So the fibrillar structure can be of different types. You can have a very straight fibril, which here it's called the linguini type, or you can have a curved fibril, which here they are calling it the spaghetti type. So this protein is polymorphic in nature. The aggregation that is forming can be of different types. And each of this type will have different functions. They are both toxic to the body, they are both causing diseases, but the symptoms and the disease type are different depending on the polymorphic structure. Now, due to the formation of this kind of aggregates, one of the common diseases that happen is Parkinson's disease. And what happens here is that in the neurons of the brain, in the substantia nigra part, the protein gets aggregated. And what that it causes is that due to aggregation of this protein, there is something called Lewy body shown here that is made, which is made up mostly of beta sheath structure. And whenever this kind of beta sheet aggregate is formed, the communication between neurons of the brain is hindered. So suppose you have normal neurons where one neuron is easily conducting the nerve signal to the next neuron. But whenever you have aggregation of the alpha-synuclein protein, you have formation of Lewy bodies, and these Lewy bodies are deposited on the neurons and they are preventing the conduction of nerve impulse properly from one neuron to another neuron. So you can see this is the alpha-synuclein protein. When it forms amyloid fibrils, they appear like fibers in nature. But as it was seen from CD and FTIR, these fibers are actually made up of aggregates of beta sheets. And this is the root of the disease. Now, basically, we will talk about another NMR technique, which is dynamics-based spectral editing. So in this, what is done? So you can have a protein which has a portion of the protein is static and a portion of the protein is mobile. So for the mobile part of the protein, and solution state like NMR can be done, and for the that is J coupling, and for the static part of the protein that has aggregated into some kind of a beta sheet aggregation structure, for that you can do solid state like NMR, that is dipolar coupling to transfer the magnetization. So basically, you can study the static part of the protein by using experiments. You can study the mobile part of the protein by using experiments like INEPT or INTEPTopsy. They will give you ideas about which are the amino acids. So suppose you have a protein that has a static part and a mobile tail. So this part of the protein can be studied by this INEPT or INTEPTopsy, that is the solution state like NMR. And they will give you that which are the amino acids which are connected by J coupling, that is they are in the flexible part of the protein. And for this part of the protein, which is a static solid-like part of the protein, you can do PDSD experiments or NCACX experiment, and it will tell you which are the amino acids involved in the solid part of the protein, where magnetization is transferred using dipolar coupling. So we won't go into details of that, but you can just remember that you can do these two kinds of experiments to find out which regions of the proteins are flexible and which are static. So you can see here the sample preparation is basically there can be different kinds of sample preparation. One is where the beta sheet is uniformly labeled and it can be non-diluted, that is all the beta sheets are labeled with 13C or 15N, or it can be uniform labeling, but you are diluting it. So in the beta sheet aggregate, only one or two beta sheets are uniformly labeled with 13C and 15N, and the rest are unlabeled. Or you can have another sample preparation scheme where you have mixed labeling. So one beta sheet having 15N labeling, next beta sheet having 13C labeling, after that again 15N, and so on. So you have in the aggregate, some beta sheets are labeled with 15N and some are labeled with 13C. So this is how the samples are prepared for NMR, because we know that if we are doing heteronuclear NMR, we need to label the samples. So these are the different ways in which the samples can be labeled. We will now look at a way at sequentially assigning the amino acids using CC and NC correlations. We will just look at a short dipeptide, that is glycine serine. So if we start from here, which is a 13C spectra, suppose this is, we assign this peak to the C alpha C beta of serine. So this correlation is between C alpha C beta serine. Then if you follow the spectra to this upper spectra, which is the 15N13C spectra. If you follow the C alpha of serine in the, so we will follow it in the vertical. So this is C alpha C beta. So we will follow it in the vertical line. So this will be NC alpha. That is, it will be NC alpha of serine. Now, if we move to this spectra, which is 15N and O. So NO correlation, 15N and this is NCO. So correlation between 15N and carbonyl carbon of the previous residue. So 15N, you go to the carbonyl carbon of the previous residue. So this is between serine and glycine. So N of serine to CO of glycine, I-1 correlation. Then you come down along the vertical. This is again 13C, and this is C alpha CO correlation of I-1. So C alpha CO, so it is this correlation of I-1. You arrive here. So that gives you, so basically you are walking through the amino acid chain like this. So you're taking different 2D spectra, and from one 2D spectra, you're moving to the next 2D spectra. So suppose this is, as I said, this is the C alpha C beta of serine. If we move vertically in the same line, we will have the C alpha of serine. And if it's with 15N, then it is NC alpha of serine. So like this, we can move from one 2D spectra to another 2D spectra and sequentially assign the amino acids along the peptide chain with CC and NC correlations. There is a method called sparse labeling to enhance resolution. So basically what happens is that this is glucose. U is for uniformly labeled glucose. So in glucose, if all the carbons are labeled, you will not get a very well-resolved spectra. You can see the spectra here is kind of spread out, not very well resolved, the one shown in black. But instead, if we selectively label the C2 of glucose, you can see only the second carbon is labeled with pink. You can see the spectra is very well resolved. The peaks are so much sharper. Now, if you feed this glucose to the bacteria from which you are getting the protein, then the protein will also be sparsely labeled. It will not, so all the 13C of the protein is not labeling. Only some specific 13C of the proteins are labeled, which are coming from this second position of glucose. Then the spectra is much better resolved. You can see this is a very well resolved spectra where each of the peaks are very sharp. So this is another method to improve the resolution of these 2D experiments. Now, how do we find the supramolecular structure of this amyloidogenic fibril that is forming? Basically, proton-mediated polarization transfer is done from 15N to 13C. So suppose you have a fibrillar structure formed by beta sheet aggregation like this. HNCH experiment is done. So the polarization is transferred from proton to nitrogen to carbon back to proton. And you are only detecting nitrogen and carbon. So because we are not detecting the protons, we are calling it proton mediated, and polarization transfer is happening from H and CH. Now, what this will do is that it will tell us which of the nitrogen and carbon are close to each other in space, forming a beta sheet. So if the nitrogen and carbon are around 4.7 to 5 angstrom away from each other, then they will show cross peak in this NHHC experiment. So you can see this is the NHHC experiment. The black is one where it is mixed labeling. One second. So basically, you can doing this NHHC experiment, you can find cross correlations between the nearest residue from different monomers within the same beta sheet, and it will give you an idea about the three-dimensional structure of the protein. So far you are finding the two-dimensional, you are finding the connectivities, that is the 1D structure, or you are finding the 2D structure from NOSI. So we just saw NOSI, you are finding the 2D structure, but how do we find the 3D structure? We will do this kind of NHHC experiment, which will give us correlation between the residues that are interacting with each other in the beta sheet. So this gives you an idea about the 3D structure as well. And also we will just briefly look into membrane proteins. We have already discussed that membrane proteins have very important functions like signal transduction or acting as pumps for calcium or ATPase inside or outside the cell, and also as ion channels. But the problem of these membrane proteins is that they have very low solubility, so you cannot do solution state NMR, and they are difficult to crystallize, so you cannot do X-ray crystallography. And also we need to study these membrane proteins in the natural environment of the membrane. So somehow we need to simulate the natural membrane environment. This can be done in different ways. We can make a detergent micelle by adding detergent molecule to the protein. We can make a bicell like this, or we can make a nanodisc where the protein is kind of surrounded by two discs of lipids. But by far the most accurate representation, which is done in the most modern research experiments, is forming a liposome. So you have a huge lipid molecule, uh, and the membrane protein is kind of embedded in the middle of this lipid molecule. So this entire thing is called a liposome, and it is kind of simulating the natural environment of the protein. So if you study the NMR of the liposome, whatever structure you will get for the membrane protein is that structure which the membrane protein adopts in its natural environment when it is embedded in the membrane. Now, these membrane proteins can be of different types, like integral proteins. Integral proteins are completely integrated into the membrane. They can be just one strand or multiple strands. So there can be a single alpha helix, or there can be a bundle of alpha helices, and there can even be many beta sheets forming a structure called a beta barrel. Or you can have peripheral proteins that are just attached to the periphery of the membrane. They are not fully crossing the membrane. And that is another kind of membrane proteins. So just one second. Yeah. So one type of membrane protein that we will just very, very briefly look into is VDAC1, that is voltage dependent anion channel protein. This is a mitochondrial outer membrane or MOM protein. It is present in the outer membrane of the mitochondria, and it is responsible for transporting NADH ATP inside and outside the cell. This protein has a beta barrel structure with a very short helix inside. You can see the helix is shown in red. So in this protein, when the structure of this protein was determined, what was seen that it is So basically this is a membrane, membrane protein. So in order to find out the structure of this protein, we first have to create this kind of liposome structure or some other kind of membrane structure in order to simulate the natural environment of the protein. This was done in different ways. Here the red spectra is shown where DOPC was used. DOPC is a detergent or lipid molecule where the lipid molecules are slightly elongated. And the blue spectra is where DOPE was used. Now, if you see the structure of DOPE, we won't go into details of that. But what happens is that DOPE puts a certain pressure on the membrane. You can see this is bending inwards. So it's putting a kind of pressure on the membrane. So the structure is slightly changing based on which lipid or detergent molecule you're using to simulate the membrane environment. So it was very important to optimize the membrane environment, because choosing which lipid or detergent you're using to simulate the membrane environment can change the spectra. But after that was done, the structure could be properly obtained, and it was seen to match very closely with the structure obtained from other methods. So even membrane proteins, which absolutely cannot be studied using solution state NMR, the structure has been very accurately determined by solid state NMR. So we have covered all the lectures of the final week, that is week 12. And now I will just go into the assignment questions of week 11. So firstly, it is asking which of the following statements regarding relaxation data interpretation is false. So for this, what we have to do, we have to remember the different equations of the relaxation data. So longitudinal relaxation rate and transverse relaxation rate, that is R1 and R2, are calculated as function of frequency of hydrogen atoms. You can see that in the formula of R2, you have omega h, that is the frequency of hydrogen atom. And in R1 also you have omega h, that is the frequency of hydrogen atom. So this is true, but the question is asking what is false. Then it is saying longitudinal rate and transverse rate are calculated as frequency of nitrogen atom. And you can see in both you have omega n also. So this is also true. And D is saying NOE, longitudinal transverse rate, are calculated as frequency of hydrogen atom. Longitudinal and transverse we have already seen, and NOE also you can see hydrogen frequency is there. So this is also true. So this is the only false statement. So because it is asking what is false, we ignore these, and C is the correct answer. Why is C false? Because it is saying NOE can be calculated as function of frequency of R exchange. So you can see in the term of NOE, there is no R exchange term. There is only R1 term. And in R1 also, there is no R exchange term. R exchange term is there only in R2. So R exchange is only associated with R2. It is not associated with NOE. So statement C is false. And the question is asking what is false. So C is the correct answer. Then you have this saying, Lipari-Szabo describes dynamics through which of the following parameters? So if you remember Lipari-Szabo, basic assumption of Lipari-Szabo is that you can separate the internal motion, that is the tumbling of the individual residue and loop, and the globular motion, that is tumbling of the whole protein. So the dynamics in Lipari-Szabo is described in terms of three things: an overall rotational correlation time, tau, Tm, that describes the globular motion of the whole protein; an internal correlation time, Te, that describes the tumbling of the individual residues; and an order parameter S squared describing the amplitude of the internal motion. So it does not include folding, unfolding, viscosity, or energy, but it does include overall rotational time, you can see here. So the correct answer is option A. Then you have a question. Which of the following statements for calculating spectral density function is true? So if you remember the spectral density function, you can remember that you can see we'll go through the statements one by one. Molecules undergoing rapid tumbling. Rapid tumbling means correlation time is small. So tau 1 nanosecond correlation time is small. Can sample a wide range of frequency. You can see that is true. Tau 1 nanosecond is sampling all these frequencies. So this is true. So the correct answer is A, but we'll also look at why the other options are wrong. Molecules undergoing rapid tumbling samples a small range of frequency. This is false. We just saw it samples so many frequencies. Molecules undergoing rapid tumbling are insufficient. No, it's not, because we are sampling a lot of frequencies. And molecules undergoing rapid tumbling cannot be used for calculating spectral density function. That is also not true. There is no such restriction. So option A is the correct answer. Then you have a question saying, range of NOE values for 13C and 15N are what? So now we will go back to the equation of NOE, where NOE is calculated as the intensity of saturation by intensity of unsaturation. If you remember, we do two experiments. One where the RF pulse is added, that we are calling the I saturation, and one without the addition of RF pulse, where we are calling I unsaturation. And the NOE comes out to be 1 plus sigma XH by R1 into the ratio of gyromagnetic ratio of, the ratio of gyromagnetic constant of hydrogen and the heteronucleus. So sigma XH is the rate constant of cross relaxation, that is between X and H, and R1 is the longitudinal relaxation rate. If this NOE is calculated, if you remember, we studied this, is 15N has NOE values from 1 and -4, because 15N has a negative gyromagnetic ratio, and 13C has NOE values in the range of 1 to 5. So the correct answer is B. 13C range is 1 to 5. 15N range is -4 to 1. Correct answer is B. Then the question is asking, the scheme for a 2D heteronuclear relaxation measurement involves which of the following? So if you remember the scheme for the 2D experiment, it starts with a preparation time where you create the desirable initial coherence. Then you have a delay time of T. You can see there is a delay time here. This time T of, so creation of desirable coherence, this is part of the scheme. There is a delay time of variable length to allow auto-core relaxation or cross-core relaxation. Then you have a time period T1, this time period, to label the residual coherence by chemical shift of the heteronucleus. Here it is 15N. Then there is a magnetization transfer back to 1H. You can see magnetization transfer back to 1H. Then the 1H signal is acquired. You can, if you remember, in solution state NMR, which we have been doing so far, the FID is always collected on 1H. So 1H acquisition is done with broadband decoupling on heteronucleus. Acquisition of the proton signal with broadband decoupling of, so this is part of the 2D scheme. And finally, there is a delay between the scans, because you have to allow the magnetization to come back to equilibrium before you repeat the experiment. So all A, B, C are all part of the scheme of the 2D heteronuclear relaxation experiment. So the correct answer is D, that is all of the above. Then you have a question. Which of the following statements is true for correlation time? So if you just think of the definition of correlation time, it is the time taken for a molecule to rotate 1 radian. And if you convert that to degrees, it comes to around 57.3 degrees. So you can see which of the following statements is true for correlation time. It is option D, which says it is the amount of time a molecule takes to rotate 57.3 degrees. So the correct answer is D. Then you have a question saying correlation time depends on which of the following. So if we remember what we studied about correlation time, we can see that correlation time, so if you see the last point, correlation time depends primarily on molecular size. So big molecules tumble slowly, so they will have a large correlation time, and small molecules tumble very fast, so they will have a small correlation time. So it primarily depends on the molecular size and shape. So it does not depend on the NMR machine at all or on the pulse sequence. It does depend on solvent viscosity and temperature a little bit, but so it can be option A or D. But if you see, if you have to choose one option, it actually depends on both molecular size and temperature. You can see temperature is a factor. But if you have to choose one, you should choose molecular size because that is the primary factor that affects the correlation time. So the correct answer is option A. Then you have a question. Fast and slow timescale dynamics refers to which timescale respectively? So if you remember our previous class, the fast motion timescale is from picosecond to nanosecond, and the slow motion timescale is from microsecond to millisecond. And the magnetization exchange spectroscopy is studied from millisecond to second. So here, if we look, fast should be from picosecond to nanosecond, that is option A. And option A also says that slow is from micro to milli. That is the correct answer. So the correct answer is option A. The next question asks, motion of aromatic acid side chains fall under which time scale? So if we look at the different time scales, if we have bond vibrations, it's a very short time scale of femtosecond. If we have the rotation of a methyl group or the motion of a loop or a side chain, that is from picosecond to nano or microsecond. And larger motions of whole domains can range from microsecond to second. So if you look at the options, we are talking about aromatic acid. So this will fall under side chain rotamers. It is ranging from pico to, we can say, nano or micro. So the closest answer is option D. That is picosecond to nanosecond. You can see picosecond to nanosecond. Sometimes it might go to micro, but there is not too many rotations in the microsecond time scale. So the correct answer is option D. The next question is asking, relaxation data interpretation can reveal information on which of the following aspects of molecular motion. So you can just remember that the relaxation information gives idea about protein dynamics. And this can be of different time scale. If it's something like a loop or hairpin closure, which is a very fast time scale, then you will need to do RDC or CPMG experiments. If it is of time scale that is even faster, like only the movement of the backbone or a side chain, then you will need to do R1, R2 relaxation experiments or NOE experiments. If it is a slower time scale, intermediate time scale like secondary structure formation, you can do HD exchange. And if it is an extremely slow time scale like protein folding, that is 1 millisecond to 1 hour or 1 second to 1 year, it has to be diffusion NMR. But the relaxation data, it will give you information about protein dynamics. That is the basic point. So it is not the 3D structure or the function or the secondary structure, but the backbone dynamics that you get information on from the relaxation data. So the correct answer is option A. you can see the backbone dynamics. The backbone dynamics, you get the information from relaxation data R1, longitudinal relaxation, R2, transverse relaxation, and NOE. So it is backbone dynamics, that is option A, which is the correct answer. That is all the questions we have. So I've covered all the questions of assignment 11. I have discussed all the lectures of week 12, and this video I'm recording and posting a little out of schedule because um, I had asked to postpone the class. But the video, as always, will be uploaded. The slides will also be uploaded. We will have just one more class on 21st October, that is this Monday, where it will be a revision class. I will go through all the classes so far and discuss problems on all the concepts. So I'll end the class now. I'll stop the recording and hope to see you in the next class.